Hello and welcome to my presentation on analyzing a dental ultrasonic scaler as a control system. My name is Michael Bain and I am a third year mechanical engineering student at Northeastern University. My project motivation is that my family has a lot of dentists in it. My father currently runs the family dental practice in Cambridge, Massachusetts, which my grandfather started in 1958. My uncle worked for that practice until he retired in 2020, and currently my sister is a lieutenant in the 2nd Dental Battalion in the United States Navy. Here you can see a brief video of an ultrasonic scaler that my dad uses in his office. There you can see the tip, and now you can see it functioning with the water stream there. Okay, this is my control system ordinary differential equation model. Here in the bottom left, you can see my equations with all the parameters being defined here. Please pause. I don't have time to explain all of them, but here you can see a simple diagram of what's kind of going on in that tip. The main points to notice is that there are mechanical dynamics, phase dynamics, and thermodynamics all coupled into one system. Here you can see the state vector, input vector, and output vector, which each of the states, inputs, and outputs defined here. The modeling assumptions were relatively simple. The first one was that the scalar tip was modeled as a single degree of freedom mass spring damper system, kind of to ease up calculations. The second was that the scalar tip and transducer were approximated as a single lumped mass. The third was that the electric circuit dynamics were neglected. Fourth, fluid loading and tooth contact, which can be unpredictable, were approximated using a smooth nonlinear damping term. And finally, the thermal effects were modeled as a single state, sufficient to capture dominant resonant drift behavior during operation. Here you can see my equilibrium point and CLTI system. As I mentioned before, there were 3 coupled subsystems, and for each of these subsystems, the equilibrium point was found and then input into this vector form. One key thing to note is that I did take one further interesting point, putting this angle to 0, thus eliminating that trigonometric term. Here you can see the linear form with my state matrix, input matrix, and output matrix defined there. Stability was found to be only marginally stable because although the mechanical subsystem's eigenvalues were always going to have negative real parts, since M, C, and K are always going to be positive in normal operating conditions, the eigenvalues for the thermal subsystem did have a 0 eigenvalue. Therefore, that makes it not asymptotically stable, but the entire system is only marginally stable. This is the closed loop law using the state feedback controller of this form. And we can see here on the diagram that all states do converge to 0 as time goes on. Here you can see the linear state estimator. The eigenvalues were chosen so that they were faster than those controller poles on the previous slide, ensuring a more rapid convergence, as we can see here in this graph. Here you can see the estimator-based control. Again, all states converge to 0 using these equations and this combined dynamics using the estimation error here. Here you can see the estimator-based control of the nonlinear system. Here, that estimator-based controller designed from the linearized model on the previous slide was applied to the original nonlinear system, as you can see here. The observer still uses that same linearized model structure, and the same control law remains here. And here you can see that figure of the closed loop response. For the disturbance analysis, the disturbed model was set to be this, with these particular definitions. This models a sudden change in external loading, which could be caused by additional resistance due to contact with the tooth surface, local fluid loading, or a momentary change in the mechanical operating condition. Again, the same estimator-based controller from section 4.3 is still applied, and here you can see that disturbance applied here with not a very large effect in the regular nonlinear response. The open loop analysis, you can see here with the inputs here and then the open loop steering here. And then the nonlinear state estimator, again, uses this measured output with the estimator as defined here with the estimation error here, and you can see that all states converge to 0. So in conclusion, this paper presentation developed and analyzed a nonlinear continuous time control model of a dental ultrasonic scaler, incorporating coupled mechanical, electrical, and thermal and fluid dynamics. A physically meaningful operating equilibrium point corresponding to resonant vibration was identified and used as the basis for linearization. As we saw, full controllability and observability was found, and the stabilizing state feedback controller and a Leuenberger observer was derived. The controller remained effective under moderate disturbances such as increased mechanical loading and temperature-dependent resonance drift. Future work could factor out some of those assumptions we made. For instance, you could include a multi-mode vibration effects or a more detailed fluid structure interaction that would all add complexity to the analysis and lead to a more substantial and more accurate analysis. Overall, the results of this paper project showed that the control analysis can be effectively applied to ultrasonic dental scalers, leading to improvements in efficiency, performance, and safety. And with that, I'd like to thank you for listening to my presentation.